Hey there, I'm Red Dragon Web Design. We are doing a series where we do CodeWars problems in NASM assembly language. And today we are going to do the problem get ASCII. So we need to create a function that it receives a character, a char, and it outputs an integer that is the ASCII value of the char. So let's get started. Alright, so let's go to the kata page on CodeWars. This is their list of exercises, and we're going to type get ASCII. Enter. Get ASCII value of character. This is the one we want. We're going to click on NASM, which is, of course, another name for assembly language. And then it gives us the problem here. So I'm going to reset this. Alright, so right away we see our very first clue as a comment in the problem. They have given us the sizes of everything that we need to pay attention to. This is something that can be tricky in assembly language CodeWars problems. If they give you any sizes, make sure to pay attention to that, because that is the sizes they want you to work with going into the function and coming out of the function. So right away they gave us a size of int here. So we know right away that we need to use the e prefix for that. It needs to be an int, which is 32 bits. So let's see, that one would be e. That's the output of the function, so that's going to go in the A register. So we want that one to be EAX. And then this right here is going to be the input, and this is going to be coming into the problem. So right away, we know the first argument coming into a problem is going to be DI, the destination index register. So we want DI, and then if we only want it to be 1 byte wide, we want to suffix it with L for low. You guys may remember this table from the very first video. This is the table of all the registers. Remember, a register is like a variable, and each row in the table is one register, and you can change the size of the register depending on what you name it. So what I did over here is for the size of int4, which is going to be outbound, it's going to be the output of the function. And then this one, of course, is the input. Because it's the output, we know it's always going to go into the A register. So I looked on this table where we have the A register, this whole row. Anything in this row can be that register. Each column is a different size. So in the case of an int, we want 32-bit. So that's why I'm calling it EAX. The reason we know it's an int is because it says int right here, and it's also telling us the size of the register in bytes. So 32-bit is equal to 4 bytes. So that's why that's EAX. And then for this other one, it's, like I said, it's the destination index. And the reason I know it's the destination index is because of this slide from our first CodeWars number 1 video. The parameter order of the input for the function, the first input coming into the function is always going to be this DI register. The second one's going to be SI, then DX, CX, R8, R9, etc. So, knowing that, we know it's going to be the destination index register, DI. So let's find DI in our table. Here we go, this whole row. And then what size do we want? We want 1 byte, 8-bit. So that's why we're going to do DIL. And L stands for low. I'll explain that a little more later. For now, for the 8 bits, just always use L at the end for these first couple. There's also H you can put at the end, but that's a little complicated. Explain that later. So before we go any further, let me explain a little bit more about register naming. I kind of said the names in the first video, but I didn't go into detail. So let's check out this slide. This is a list of the most common registers that you'll be dealing with. Remember, there's only a fixed number of registers. Each of these is like a temporary variable. If you have more temporary variables than registers, then you need to reuse your registers. So let's just go row by row here. And I'm going to use the widest possible name for the example here, the 64-bit, which begin with R. So RAX is the A register, our BX is the B register, C RCX is the C register, etc., etc. Also have a D register. And then you have these two special ones, the base pointer and the stack pointer. Be careful with these. In general, you do not want to use these. You only want to use those if you know exactly what you're doing. You don't want to use those for normal variable assignment because they have the contents of that register. Their value is it's significant to something else that's a little complicated that I'll explain later. So just know that these exist, but don't actually use them. And then SI for source index, DI for destination index, and then you have general purpose registers 8, 9, 10, 11, 12, 13, 14, and 15. So you have a decent number of registers on a 64-bit machine to work with. Now let me describe each register. A lot of them have specific uses. If you run certain instructions, like let's say you do a multiplication instruction, mul, then it will kind of default to certain registers. It'll put its results into the A register, for example, automatically. Like you can't even really tell it where to put it. It'll put it there automatically. So some of these registers, they receive certain values from certain instructions. So that's kind of the inspiration for their naming. If they are linked to certain instructions, that kind of determined what their name is. Maybe not for these first four, but especially for source index and destination index. That has to do with string instructions that I'll teach you a little bit later. And then just know that these first four registers also are the default register for certain instructions. A and D are involved in arithmetic instructions, especially multiplication and division. That A register, also addition and subtraction. And then know that the C register is almost always used for loops. Like if you have a for loop and you have like int I as the counting variable, it will usually end up being put into the C register. That's a good practice. Alright, so with all that said, let's get back to the problem. So remember, our input is this char. So our input is DIL, and our output is going to be this int, which needs to go into EAX. So why don't we try that? Of course, the way we put a value, the way we move a value from one register to another is we use the move command. So we're moving into EAX DIL. And that's it. The problem should be done, right? Let's give that a test. And we have an error. Invalid combination of opcode and operands on line 8. So the reason we're getting this error is because in assembly language, if you change register sizes in your instruction, if the operands aren't the same register size, you need to use a special instruction, which I'll teach you about in a minute here. So if you're going from a 1-byte register into a 4-byte register, you cannot use just a plain move command. You will get an error. Alright, so quick review. If you want to take a value and change its size, you just use the corresponding register size. So we talked a little bit about this already. Here's a quick review of it if you want to take a look. But what I'm going to talk about now is how you move a small value into a big register. To do that, you need to use a special command. You need to use movzx or movsx. And what that does is it's going to pad the smaller part of the value with numbers, with zeros or ones. I'm going to say zeros or F's here because F's in hexadecimal are equivalent to ones. And the way you know which one to pad it with is if it's an unsigned value, you'll want to pad it with all zeros. movzx is the unsigned version of this command, this instruction, and then movsx is the signed version. So in that case, it'll take a look at the sign of the old, of the original, of the smaller value, and then it'll decide based upon that sign whether it wants to pad it with zeros for positive numbers or F's for negative numbers. So movzx is for unsigned and movsx is for signed. So in our case up here, we're going to want to use movzx because a char is usually unsigned. Technically in C you can make it signed, but for everything we're going to do, we're going to assume it's unsigned. We want to pad it with zeros. So this command needs to be movzx. And why would we pad it with ones if it's negative? Well, very simple. It's because of 2's complement. You may remember we talked about 2's complement in a previous video. And the way 2's complement works is whenever you're counting up, you count normally. Let me zoom in on this chart here for you. Whenever you count up, 0, 1, 2, 3, 4, you count normally. But whenever you count down, most of the bits actually flip to 1. So -1 is equal to all 1s at the bit level in base 2. And then each number you count down subtracts from that until you meet in the middle of the range. In the very middle of the range. Alright, let's talk about automatic zero padding for a second. Under what circumstances will the processor do this conversion for you? Because sometimes it will and sometimes it won't. So let's say you put a number into EAX. What is going to happen to the rest of the data in that register? What's going to happen to the left half of the number, the other 32 bits, the upper 32 bits? In the case of this E prefix, the 32-bit registers, it's actually going to zero all those out for you. You don't need to use a movzx command or anything like that. It will zero them for you. And then RAX, of course, 64-bit, uses the whole width of the register, so that's not applicable. We don't need to worry about that. But it's a little bit tricky because these lower registers, for backwards compatibility reasons, if you were to put something into AL, for example, if you were to put a char into AL, the lower 8 bits, it would actually not do anything to the rest of the bits. Whatever they were before AL was filled with that char, they will remain. Now, as proof of that and as a demonstration of that, let's do a quick test. I've opened up SASM, which is my debugger program for assembly language. We'll talk more about how to use this in combination with CodeWars in a future video. But for now, I'm going to use it to set RDI to all ones, well, in hexadecimal. We can just make this all Fs. 1, 2, 3, 4. There, literally all ones. In binary, all Fs in hexadecimal. We're going to set 64-bit all ones, and then we're going to put a 0 in it, and we're going to see if it changes any of the other bits. So let's take a look. We'll hit our debug button. This will start the step debugger. We'll start stepping through. This is going to set RDI equal to all Fs. As you can see, RDI over here in our register watcher, it's all Fs. And then now we're going to move in 1 byte 0. So that should change these bottom 2 slots here, 1 byte wide. It should change those to 0. And the rest of them, because this is a low numbered register, it should remain 1s or Fs. There. As you can see, the only thing that changed was the first byte there. So this is what you need to be careful of, and this is why we're talking about the movzx and movsx commands, and this is also why we're talking about what these registers do by default. Because if we change this code from DIL to EDI, this will be a 32-bit version. You may recall on the slide over here, the 32-bit version zeroes the hidden part automatically. We don't need to use any special commands. It zeroes the hidden part. So now when we execute this, even though we're only moving in 32 bits of data, this right half of the FFFFFF, it should actually zero the entire thing. So let's check this out. Let's prove this with some step debugging. I'm going to hit F11, start stepping. This is going to set RDI to all Fs. And then now we're going to move in 0 into EDI. And watch this when I hit step debug. And it has gone back down to 0. So that's how that works. Just be mindful of that. Now, one tricky thing about this problem before we go ahead and submit our final solution is the first time I did this problem, I actually tried a different approach. I actually tried something where I did the equivalent of if the character is greater than 255, I'd return 0. Otherwise, I would return the character. So that was because I didn't know the movzx command when I first did this problem. This was my way to try to get around it, but they actually wrote a test case. They're very clever. They actually wrote a test case that really tripped me up for a long time. They actually don't want you to return 0 if the right half is above, if the char is above 256. They want you to return, they just want you to chop off the left half of the char and return whatever the data on the right is. So my approach did not work. Pretty much have to use the movzx technique, or you need to use a different technique to truncate that left side. The other technique you could use is the AND command. If you are familiar with logical AND, any kind of bitwise commands, you can use a bit mask, 0, 0, 0, 0, 1, 1, the 2 bits you want on the end there. You could use a bit mask, and what that does is that only lets, let's say our value of the register, of the input was 10, 10, 10, 10, and we only want those left 2 digits. The way logical AND works, if you do 0, 0, 0, 0, 1, 1, it's a mask that only lets those 2 digits fall through. So that would be one approach. You could move the char into RAX, which is the solution register, the output register, and then you could do AND RAX with 0 FF. FF and hexadecimal would isolate the bits that we need for this. It would isolate exactly 1 byte of data on the right side. So that would be one solution. And then, of course, the canonical solution, the default solution, the solution that they're probably looking for here is just simply doing movzx, EAX, DIL, like we typed out earlier. So let's do that real quick. We actually haven't submitted this yet, but we typed it earlier. Remember, we're taking the 1 byte and we're putting it into 4 bytes, and we're padding it with zeros. So let's do this real quick. Bam, pass the test. Attempt. Alright, we passed all 356 test cases. Don't forget to hit submit one final time. Then I'm actually going to do view solutions because I don't want to submit more than once. I don't want to spam their submissions because you can actually submit more than one answer. And remember, we talked about this in the last video, you always want to take a look at the solutions. That's how you find, that's how you make sure you coded it well. That's where you do all your learning. That's where you see if you missed a library function you could have used. That's where you make sure your algorithm is nice and fast. So the best practice answer here is exactly what we did. movzx, EAX, DIL. Let's take a look at some of the other ones here. I'm actually going to unvote that. That's not really the best practice here. This guy used the AND technique that we talked about. He used a bit mask of FF to isolate that last byte. Here's my original answer. And this one's pretty straightforward. There's not too many different variations. But for a bigger problem, you'd see more variations. And you could learn a lot from looking at the answers. Anyway, that's all for today. I hope you learned something about registers. I hope we kind of built on the knowledge that we talked about in the first video, and I hope you familiarized yourselves with the movzx and the movsx instructions. If you enjoyed the video, please like and subscribe. And as always, thank you. See you soon. Bye.